In this video, we will start our section on nuclear chemistry with a review of the nucleus and element symbols, and then introducing nuclear reactions. The nucleus consists of nucleons. These are the particles in the nucleus. So this will be protons, which have a positive charge, and neutrons, which are neutral. These are held together by the strong force. This is a very short range force, so only 10 to the minus 15 meters, but it is so strong that it dominates electrostatic repulsion between the protons. So if you ever try to take a magnet and stick the two plus sides together, you know how hard this can be. The strong force is strong enough to overcome this repulsion, but it only operates over very short distances. Remember, the number of protons is also going to dictate the identity of a given element. So let's look at this following element with the symbol 56 over 26x. This is going to represent an element with what? And the correct answer for this one is D. And as a reminder, here's how we will get that answer. So with this symbol, the A is going to be the mass number. Remember, this is the number of protons and the number of neutrons. Z is the number of protons, and then X, whatever symbol is actually there, is the identity of the element. So for that particular question, this was the symbol that we were given. So Z is the number of protons. This is 26. To get the number of neutrons, this is going to equal A minus Z, which is going to equal 30. So those are 30 neutrons. And then if we wanted to identify this element, we'd find the element with the number 26, and we looked it up, that would be iron. Electrons are relatively light. This section is the one time in chemistry that we will pretty much ignore electrons. These aren't going to contribute to the mass number. And when we're talking about nuclear chemistry, remember the electrons aren't in the nucleus, so we will leave them out of most of this discussion. So if we go ahead and form a plot of the neutrons versus the protons in the nucleus, and we look at the stability of these different nuclei, we get something that looks like this graph on the right. So you can see that we have these red dots here on this chart. These will be stable nuclei. So if we have atoms with that number of neutrons and protons, they'll be stable and not degrade over time. If we have these light blue dots, these are isotopes that we'll see occurring. So things with the protons and a number of neutrons, but these ones will spontaneously decay. Outside of even these blue dots and these regions, these nuclei are so unstable that would never actually observe. You will notice that lower on, the ratio that we need is a 1-to-1 ratio for neutrons and protons. This gives us enough neutrons with these plus charges for the strong force to hold the nucleus together. As we increase the number of protons, we need a higher ratio of neutrons and protons. So we go above this even line, and we can think about why that might occur. As we can imagine, as we get a bigger and bigger nucleus and we start packing more of these together, the distances are going to increase. And so because they're going to increase and the strong force is only strong over very short distances, we're going to need more neutrons in that space to help overcome the force. This is sort of a generalized explanation of this. The details are fairly complicated, and if you're really interested, that would be the purview of nuclear physics. So nuclear chemistry is going to study the reactions of these unstable nuclei. Unstable nuclei are going to decay to make new nuclei, and they'll keep doing this until they get to one of those stable red dots on the graph. There are several types of reactions. We will go over several of them. The first one we're going to look at is alpha decay. So if we have this nucleus, in this case uranium-238, this will release an alpha particle, which is a helium nucleus. So you'll see it written as 42HT. Sometimes you'll also see it written as 42 alpha. So it will release the helium nucleus, and then we get this new nucleus from the uranium, which is a thorium nucleus. This equation illustrates some features of these nuclear reactions. So first of all, you'll see that we are showing A and Z for all of these species, and that the A and Z on the reactant side equals the sum of the A's and the Z's on the product side. So if we look at the sum of all the A's, that's going to be 238. on both sides, and the sum of the z's is going to be 92 on both sides. So when we are balancing nuclear reactions, what we are trying to balance is the A and Z on both sides of the equation. The next reaction we'll look at is beta decay. So in this case, if we have carbon-14, this is going to release a beta particle. So this is written as 0 minus 1, E minus, because a beta particle is essentially an electron. You may also see it written like this, or like this. And as I mentioned, since for nuclear chemistry we're only dealing really with things in the nucleus, we'll often see sometimes these compounds written without even their charge. So in this reaction, we can see that the A on this side is 14, the Z is equal to 6. And on this side, the A is going to be 14 plus 0, so the A is still equal to 14. And the Z is going to be 7 plus negative 1, which is equal to 6. So we have the same A and Z on both sides. You'll notice with the beta decay, we have changed the element. So in order for this to balance, the Z had to increase. So we went from carbon to nitrogen, and we have made this ratio of A to Z closer for this beta decay reaction. We can also see that when we have balanced this A to Z, we can change the types of particles that we have. Since Z changed, that means we changed the number of protons. And while A stayed the same, with Z changing, that means in order for the total mass number to stay constant, we had to lose a neutron. So another way to think about beta decay is converting a neutron into a proton and an electron that gets released. Again, the atomic number increases, but the mass number will stay unchanged. The next reaction we'll talk about is positron emission. We're going to release a positron in this case. This is a particle that's very light, like an electron, but instead it has a positive charge. This can also be represented like this as a positron. Notice that it's very similar to the beta particle or electron, except here it is a 1 instead of a minus 1. And here we can think about this as being the conversion of a proton into a neutron. So the atomic number decreases as we convert this proton to a neutron, but the mass number will stay the same. The next reaction we'll talk about is electron capture. The idea of this is that we would capture an electron around the original core nucleus and then convert it to a proton and a neutron. So the equation would look something like this. So notice for this one it's a little different because as a capture, the electron is on the reactant side. And here the atomic number will decrease. We have the minus 1 in the bottom. We'll get the 12 on this side. But again, the mass number will stay the same. We have the same number of particles in the nucleus. The last one we'll talk about is gamma ray emission. Really, this is a part of almost every nuclear reaction, but sometimes we mention it specifically, and this is when an excited nucleus is going to release energy. So a gamma particle is another way to talk about a photon. We can see it has no mass number, and it has no Z. And we also see this little asterisk. So you'll see these written on compounds that are in an excited state. So what this equation is just saying is that we have an excited thorium, and as it relaxes, it's going to release a photon. We've seen this before, talking about emission of photons from other excited states back in our first part of chemistry when we talked about excited nuclei, and then we also talked about it a bit when we were talking about metal compounds. Because all we're doing is changing the energy state, we're not going to change the mass number or the atomic number. For this particular reaction with thorium, it's just interesting to note that this releases 50,000 electron volts. So unlike some of the excited states that we've seen, the thorium that we get at the end of a nuclear reaction has so much energy that it would release the same amount of energy as almost 17,000 blue photons. So with some practice using these equations, you can look at the one for electron capture and think, what would electron capture transform potassium-40 into? And so we'll see the correct answer for this one is C. For doing this, we'll want to set up the reaction, so 40, 19K. And it's an electron capture, so we'll put our symbol for the electron, and as capture, this is as a reactant. And then as the products, we will make sure we balance the A and make sure we balance the Z, so those together will be 18. We'd look up 18 and see that this matches argon, and would get that as our electron capture product with this potassium 40.